So in the previous few classes, we have seen how the convolution operation works. We haven't seen how to connect this convolution operation with neural network and how the weights in case of CNN gets updated, right? So those are the two areas where we will throw some light today. In your screen, you see there is a distinction between how the thing goes in feed forward fully connected network, that is in the right hand side, and in the left hand side in how the things goes in case of CNN. Okay, so in uh, fully connected network, feed forward fully connected network, we consider all the input to compute the value of neuron. Okay, this is clear, I guess, right? Whereas in case of CNN, we consider only neighborhood points of input. Further in CNN, we compute the multiple such output in one go using different kernel. Any doubt on in this statement?
Yeah, can you repeat the statement once again?
Yeah. See, this is a feed forward network, right? Feed forward, fully connected network. Okay. Now, this is your input layer, right? And this is your hidden layer. Now,
Yeah.
every neuron in this hidden layer is connected to every other neuron of input layer, right? So if suppose I'm having total n number of neurons in my hidden layer, in input layer, so this neuron is connected to n number of neurons of input layer.
So why are you calling the input layer as neuron and input is just input, right?
Input layer, I'm saying.
Input layer means the first layer, right?
Yes, this is the
Yeah,
first.
yeah, 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 yeah. Agreed.
Okay. So the point which I'm trying to establish is every neuron in case of feed forward fully connected network, it is connected to every other neuron of its preceding layer. Similarly, this neuron will be connected to all the neurons of this layer.
Yeah.
Right? So let us take an example here. I'm having an image, okay, and that image is 30 cross 30 cross 3. So this is an RGB image, and the dimension is 30 cross 30. Now, if we have to solve this problem, if we have to detect that image using feed forward network, how we would do is, this image dimension is how much? 30 cross 30 cross 3, right?
9,000?
No,
No, sorry. That's the
this much number of pixel, right? Right? If this is the dimension of my image, this is the total number of pixel I'm gonna have.
yeah.
Okay. So what I am gonna do if I have to solve it using feed forward network is I will flatten pixel to create one big array, and this array will have those 2700 number of pixels.
Yep.
Right, and I will put those 2700 number of inputs to my input layer. So this my input layer will have neuron, and the count of that neuron will be 2700. Right?
Yeah.
Okay. Now, if the same thing I'm doing using feed forward network, sorry, CNN, right? So how? So this is my input layer. Same information I'm having here also, but I'm stacking in a different way. Instead of flattening, what I'm doing is this is considered grid as 30 cross 30 corresponding to one channel. Similarly, I'm having another grid for 30 cross 30 and another grid for 30 cross 30 for red channel. Okay. Now you'll see that if I have to compute one neuron of hidden layer, right, I am relying only on some few number of neurons. I need not to consider for all the neurons of this layer. I will rely only over the neighborhood points only, right? And that neighborhood point, this is depending upon the size of your kernel.
Hmm.
right? So the point which I'm trying to make here is, in case of feed forward network, in order to update one neuron, you need to rely on all the neurons of subsequent layer. Whereas in case of CNN, in order to update one neuron of hidden layer, you need to rely only on few neurons of previous layer, and that few neurons is nothing but the neighborhood neurons, right?
But you see, when yesterday you were talking about this input is this much, and then the output is will be, you will run this kernel across the image,
Hmm.
and it will reduce it, right? So
Hmm.
this reduced matrix that we are getting in the form of that output, is
Hmm.
that the output of the CNN network, or this is like
No, no.
we are processing the input and then giving it to some network?
Yes, I'm just processing my input layer and I'm getting the hidden layer, like the way we are having in feed forward network, right? In between input and output layer, we are having lots of hidden layer. So same thing will happen with your CNN also. This is your input layer. This is your final output layer. In between that, there will be lots of hidden layer.
So, but then even in the other case here also, the input layer is still 2700, right? The hidden layer is becoming smaller.
The hidden layer is becoming smaller. But my point is, see, here in case of feed forward network, to compute this neuron, right?
Yeah,
We were relying on all these neurons of
yeah,
input layer, right?
yeah,
Because it is connected to all these neurons. Whereas
yeah.
in case of CNN, this neuron of hidden layer, it to compute this neuron, we need not to rely on all the neurons of input layer. We just need to rely only on few neurons, which will be decided by your kernel size,
Okay, okay. Now I understood. Yes, that's true.
right? So the only point is, if we are relying on lesser number of neurons, that means that there will be lesser number of weights to deal,
Yeah.
right? So from this, what we can conclude that the computation that is going on in case of CNN, it is a lot cheaper compared to feed forward network,
Yeah.
right? So this is a one benefit of using CNN for image problem. Why we prefer to use CNN in case of image problem is because typically image is a high dimensional data, right? If you're gonna use feed forward network to process that high dimensional data, it will be computationally very expensive. Whereas CNN provides a better way of handling this high dimensional data with efficient computation. Do you agree with
But
me?
but Ashutosh, even though what you're saying is correct, that this one neuron in the hidden layer will take less input,
Hmm.
but then overall, will it still not be the same, because all these neurons in the hidden layer,
Hmm.
they will be taking these individual sets of neuron from these each of these boxes, right?
Yes,
So will it not become then same, or you're saying that actually no, it is, there is a difference
there is a lot
in terms
difference.
of in terms of time consumption?
Yep, there is a lot difference. You can relate this network with this network, right? This is the so this both network are actually the different representation for same thing. They both are neural network, right? It's just that
Yeah,
here it is CNN, here it is feed forward network.
yeah.
Right? Just for time being, just think that you are given only input layer, right? So this is your input and this is your input here. Let me
Hmm.
clear stuff. Uh, So just consider that for time being, somebody has given you only input layer, this one and this one. Okay. Now next thing is we have to compute the neurons of hidden layer, right?
Yep.
Right. So if I want to compute this neuron, I will be doing calculations over all this neuron,
Yeah,
which is n,
yeah.
right? Similarly, in order to do computation of this neuron, I need to do computation over only a small portion,
Yep.
right? Similarly, for this neuron, I need to do computation over n neurons.
Yeah.
But here, if I want to compute this neuron, I need to rely only on very small portion,
Yeah.
right? So you see how the computation of each neuron is very cheap in CNN compared to feed-forward network. So similarly, if I have to do computation for all the neurons of my first hidden layer in CNN, I always need to deal with very, very small chunk of data. So here, if you see in each computation, I'm relying on n neurons. Here, I'm relying only on, depending on n divided by, let's say, 10 to the power, some huge number.
Yeah, I think yes, it's absolutely clear that obviously for every neuron in the hidden layer, all the 2700 are being used, but in CNN, only small set is used based on
Correct,
the kernel size.
correct, correct.
Okay, yes, it's clear.
Right. Okay. Now, moving ahead. Okay. Now, there's another distinction between CNN and feed-forward network. The reason why I'm giving stress on this point is this is a very commonly asked question in an interview. The question is, although feed-forward network can be used for computation, for classification and object detection task of images, why we specifically rely on CNN? Right? And we have seen that when we did hands-on on MNIST data, we created a feed-forward network for detecting those numbers, digits between 0 to 9, right? The other distinction between your CNN and feed-forward network is, again, you just consider that is a number 2, and here we are having one side feed-forward network, and here I'm having CNN. Okay. Right. So this is exactly same what we have seen in the previous slide. So to compute this neuron, I'll be relying on all this n number of neurons in the previous layer. Okay. Now, whereas in case of this one, CNN, I'm not relying on all those n number of neurons. Rather, I'm relying only on small neurons, which will be decided by kernel size. Right. So this is nothing but this slide is a further extension of previous slide, although I covered the content of both the slide in the previous slide itself. But for your reference, you can look into it. There's a detailed description mentioned here. Now, the other benefit which I'm gonna say is the weight sharing. Okay. Now, again, there is an image, and this image is 4x4 image. Okay. This is 4x4 image. If I have to flatten this 4x4 image into one big vector, right? I can fold it like this, unfold it like this, where this will be 1, 2, 3, 4. Sixteen. Same here also. 4, 5, 6, 7, 8, 9, 13, 16, 12. Right? You understand, right? The positions of this pixel value. Okay.
Yes.
So I'm unfolding this 4x4 grid into this one big vector. Okay. Now, see here, the point is all this 4x4 grid is operated by one kernel, right? And the kernel weights are fixed. Okay. So if suppose this 4 pixel values are operated by one kernel, right? So what is so where is the position of these 4 pixels? This 1, 2, 3, 4, right? And just think about these 4 pixels. Where are the position of these 4?
No, those 4 pixels are not 1, 2, 3, 4, right? They are 1, 2,
Yeah,
5, and 6.
Sorry. Yeah. These are 1 to 5. This one, this one, this one, and this one.
Yeah.
Okay. Now you think about these 4 points. What are the positions of these 4 points?
11, 12, 15, 16.
11, 12, 15, 16. Correct. Okay. So the weight that will operate over these 4 pixel value, the same weight will be operating over these 4 pixel also, because the kernel is same, right? The kernel is just moving from left to right and top to bottom.
Yeah.
Yes. Whereas in case of your feed forward network, for each of your input, there was one unique weight.
Yeah.
Right. So you see here, there's a concept of weight sharing. I need not to compute n different weight in each layer in case of the way I have to do for CNN.
Yeah, you need here only 4 weights.
Yes. Getting?
And the same set of weights are being used across the whole image.
Yes.
Yeah.
Right. So in terms of weight computation also, this is very, very cheaper compared to feed forward network. Okay. So if somebody asks you the same questions, why do we prefer CNN over feed forward network for image problem? There's a 2 straightforward answer for that. The number 1 is the property of sparsity, the one which we covered in the earlier slide, where we need not to rely on all the weights of previous layer for computing the neuron of succeeding layer. The second point is there's a concept of weight sharing in case of CNN. Is this 2 points absolutely clear to you?
Yes.
Okay. So now I think we are motivated. I mean, we are motivated enough to learn this CNN because people can argue that why there's a need to learn entirely different configurations when you already have feed-forward network which is capable of solving your image problem. Now, can you quickly answer these questions? In convolution operations on an image, each transformed pixel can be compared to which component of neural network?
Layers of neurons?
No, that's not correct. I'll just give you a quick hint.
Weights?
No, the weights is also not correct. The answer is a single neuron. See, this is covered in this first slide. Each convolution operation is giving you a 1 neuron value, right, of subsequent layer. The question is in a convolution operation on an image, each transformed pixel can be compared to which component of neural network? So this is one convolution operations, right? And this is transforming the pixel value, right? And it is equivalent to the computation of neuron of subsequent layer.
Yes.
Is this absolutely clear to everyone?
Yeah.
All right. Now moving to the next topic. Okay. And now, still, this is definitely, inarguably, the statement is neural network is a computation job, right? It requires lots of computations. Even if we are relying on CNN also, there is huge number of things that we need to compute. So how people used to do CNN, I mean, people used to do image classification or object detection tasks in around 20 2010 or 2005, when there was not much advancement in GPUs and TPUs, right? Uh, where we did not have much liberty to use good hardwares. So still that time also people used to solve image classification problem. You'll you will be really amazed to know that the first image detection problem was solved around I think it was 1970s, where we did not had even the modern day computer also, right? So what technique they were using that time? The funda was very simple. Always we'll have an image or image in our input. So here I'm having this my input image, okay, and what I can do is I can apply some filter here, right? So here I'm applying an edge detector filter, right? And this is transforming my this image in this form, okay. If somebody gives me this version of this image, still I'll be able to say that this is Taj Mahal, right?
Yeah.
But the amount of energy I need to invest to identify this as Taj Mahal will be lesser if I'll think from computer point of view to say that this is Taj Mahal, because you'll see that there are very fewer pixel value here. Majority of pixel is either black or it's white. So the amount of calculation I need to do to identify this image as Taj Mahal will be lesser compared to amount of computation I need to do over this one, because the pixel density and variability is high in this image. You're seeing green also, you're seeing red also, you're seeing blue also. But when I normalize this one, or I should say when I done some transformation over this image, computationally it becomes easy to identify this image.
Yeah.
Okay. So what people used to do that time is, instead of feeding this image to their system to identify whether it's Taj Mahal or not, they used to feed this image. And this is called feature extraction or feature engineering, right? Giving the right set of representation of your image to your algorithm is actually an art, and this is called feature engineering. Because if you'll give this image to your neural network, it will take fraction of second to identify uh, that this is Taj Mahal, right?
Yeah.
So back those time, people used to apply lots of filter, lots of technique for transforming their image, and they used to put transformed image to their neural network, and that neural network used to say that what kind of category this particular image will fall to. Okay. Still now, this is a better practice. If you are solving an image detection problem, do not directly feed your RGB image into neural network. If you know that there is certain uh, filter that you can apply that can um, be a better representation of your image for neural network, just go ahead and do that. That will save lots of computation, and you'll see that the days of training will reduce to, sometimes it can reduce to minutes also, right? But how do we get to know that which particular transformations or what kind of filter I should apply to get the better set of representation of my image, right? So for that reason, still we can have some additional layer, right? So you remember we have a kernel in CNN, right? And we have assigned certain weights to that. So initially, I showed you that I can have, if I'll have some kernel of this size, we I think we've seen yesterday. Right? If I'm having this kernel, it will just detect edges of your images, right? if we don't know what should be the appropriate weights of the kernel should be, then I can keep it blank. Also, I can keep it all of my weights is X, and I'll let neural network to figure out what should be the optimal weight. Right? So typically what happens in case of image detection problem, if you want to break your problem into multiple chunks, how it operates is you give your image in one side, okay, and then neural network train does training to find the optimal representation of this image. Right? What I mean by saying optimal representation is some transformed version like this or this. Okay, and once it has identified the representation, this optimal representation is fed to final classifier. So when I say final classifier means what? I'm talking about the output layer where actually my softmax function is applied to bucket this image, the transformed image, into one of the 4 category here.
So one question, Ashutosh. So you're saying that all the layers that are going to be there in this CNN network,
Mm-hmm.
they'll be doing these performance, these tasks, right? Like converting into an edge image and then maybe applying some other, what do you say, other idea which will further refine the image or further make things
Correct.
easier, right?
Correct.
So these are the layers that are doing all these things.
Yes, correct. So precisely, if you are suppose creating a convolution neural network of 10 number of layers, the initial 4 or 4 to 8 number of layers, they will just try to figure out what should be the optimal representation of this image. Optimal representation means some version like this, which can directly fit into the classifier, and the classifier can easily detect.
Okay.
Right? That is the reason neural network is also called deep representation learning. Okay.
So do we come, does this issue is exclusively for images only, or it applies to, audio data and other data?
It applies to all sorts of your data. Right. So same thing we do in case of a traditional machine learning algorithm also. For example, are you aware about SVM, support vector machine?
No.
Okay. So just for timing, you can understand that if you are having some statistical model, some static model instead of neural network, I'm having just one algorithm which is are doing a job of classifier. Okay. So what we do in machine learning is, first of all, we have the data, we massage our data, we do some feature engineering, and we provide our transformed data to our classifier for making the prediction. Okay. Same thing happens with neural network also. It's just that we need not to do the transformation. Neural network itself will figure out what would be the best transformation for the given image by iterating over this different weights of kernels, right? And it will figure out what should be the best weights of this kernel, right? So internally, the same thing is happening in case of neural network also. It's just that we are not doing it explicitly. Neural network is figuring out the feature engineering task by itself.
Yeah.
Okay? And that is the reason sometimes people say that neural network is a black box. Because what the people do is simply they put their images in their input layer. They get the prediction in output layer. Nobody knows what is happening at between input layer and output layer. Right? Now I think you know that in between input and output layer, neural network constantly iterates over the value of weights, trying to figure out the best weight that will give the best representation of this particular image. Right? Once it has identified the best representation, it will feed into classifier. So when I say classifier, I'm talking about the output layer, which is having softmax functions that will classify your representation into one of the 4 categories. Is the entire story clear?
So CNN also does the back propagation?
Yeah, it also does the back propagation. Entire neural network trains on back propagation.
So basically CNN is like feed forward network only, except the differences you have shown, where
Yes.
the how it is convoluting, how it is that the pixel thing you showed, right?
Yes.
Like converting into single neuron. So that is the extra thing which we are doing in convolution network.
Yes.
However, the process is still the same,
Yes. Yes.
applying the the functions in each layer, and the
Yes.
final output function will be something, and then it back propagates the gradient descent, it follows, all of that is same.
Correct. Yep. That's exactly the same. There's a slight tweak when we want to do update the weights in case of CNN. I'll talk about that part. Just a minor difference, but need not to worry now. We are not there yet. Okay.
Okay.
All right. So then quickly answer me these questions. Why is a deep learning is called deep representation learning? This is something we just discussed.
The second one?
Yep, you're right. Okay. now let us make it a little bit more interesting. So we said that we need to transform this image in some other format which makes the job of classifier easier. Okay. Now we are saying that why to go for only one representation of it? Why not to see the multiple best representation of this image? So you may say that for some images, this image detector filter might work well. For some images, smoothing effect might work well. For some images, some other kind of filter might work well. So we do not know which particular filter will work well. That's why we are letting the neural network to figure out the weights. Now we are saying that instead of having just one representation, we will have multiple representation of this image, and we will stack those multiple representation together, and we will feed that multiple representation into my classifier for making prediction.
So you're saying that we are going to give the data converted using different filters?
Yes.
To the input of the classifier?
Yes.
And this input is somewhere in between the hidden layers, right? One of the hidden layers is going to be given this data.
Yep.
But will this be given in parallel, or they're given one after the other?
That's up to you. What I think is this is done in sequential way. So first of all, you will have one filter, right? And that filter will transform this image into some other kind. Then you'll have another filter that will again apply on the same image. It will transform that image into some other way. Likewise, you'll do for few number of filters, and all the outputs will stack them together.
So remember, when we first created our networks, right, we were giving these models. One of the models had the name sequential, right?
Yes.
So that means if there is a model by the name sequential, then there has to be a model by the name in parallel also, right? Where probably here that parallel thing comes into picture.
It's not like that actually.
Oh.
See, the reason the name is sequential because it is the learning is happening in sequence. For example, the output of one layer will be fed to the neuron of other layer. This will fed to the neuron of other layer. Likewise, it will go from left to right.
Yeah.
In a sequence. It won't be sequential if the output of this neuron is feeding back to the input, back to the neuron of previous layer. Right? So actually, these kind of model which where my output of one neuron can fed back to neuron of preceding layer, that kind of network is used for sequential modeling. So sequential modeling means speech recognition, mainly the kind of problem we deal with in signal processing, language translation. So all those different model you see, like for example, Google translation model, right? That is an example of neural network, and that neural network is called RNN, recurrent neural network.
But images use parallel models, right?
Sequential model. CNN
Images
is,
also use sequential model, you're saying?
yeah, this is sequential model only, right? We are not feeding the input of one layer back to the neuron of previous layer. You'll not see
No,
that.
but you did say that we are applying the different filters, so we are getting different, outputs,
Hmm,
and these outputs are applied together. So that means the one with edge detector image is also going, and then on the side the smooth filter was applied. That is also going. So are they not going in parallel all the
that
way?
that is not the meaning of parallel here. Parallel means we would so there's, first of all, there's nothing like parallel model. Okay, there's sequential model and there's another kind of model which I'll talk a bit later. The reason it is called sequential because the output of one layer is spreading to the input of another layer, which is a unidirectional,
Yeah.
right?
Okay. Okay.
Same thing is happening with CNN also. Here we are operating over input layer neurons. It is uh, the convolution operation over the input neurons will be creating the neuron of the subsequent layer. It is not like again this computation will be fed back to previous layer.
That is clear. But what I'm still trying to understand is looking at the image on the right side, right, where this kernel you have drawn. So you're
Mhm.
saying that on the single image,
Hmm.
the three different filters are being applied
Yes,
together
yes.